Okay, and these are notes in section 6.1, and these are just the first part of the assignment, as 1 through 23 odd, I think. And these are just taking antiderivatives, really. We're solving these differential equations. Just getting it up here to look at the directions, but it's pretty straightforward. It says find the general solution to the exact differential equation. So we have an exact differential equation here. dy dx equals secant x tangent of x minus e to the x. Now you could just write the antiderivative of that and put plus c and save yourself some steps if you want to. You could just say, you could go right down and the antiderivative of the secant tangent is just the secant, and the antiderivative of e to the x is e to the x. So you could just probably go from the first step to the last step and be pretty much done with it, as we did on some of those antiderivatives on our antiderivative worksheet we passed out earlier. Okay, because this is my derivative. This is the antiderivative. But we're going to be doing this a little bit later. We're going to use this technique in what we call separation of variables. So it's not bad to get used to it. So if you go from here to here, I can't really argue with that. But if we do the setup like we were going to do when we get more complicated differential equations, we're going to be doing a lot of that in chapter 6. Then what you could do is you could just put the dx over here, almost like we're multiplying both sides by dx, but we're just separating it like this. And then we would take the antiderivative of both sides by integrating, because now we know from the fundamental theorem of calculus that's almost the same. Well, it is the same. It ends up being the same as the antiderivative, and the antiderivative of that is just y. So this is an integral notation, and then this is just going to be again the antiderivative of this, so it ends up being like that. So these are a couple steps of notation that will play into we'll be doing these a little bit later. All right. So it's not a bad idea to be aware of this technique. But like I said, if you just realize that the derivative of y with respect to x is this, then you know that y must equal that. And then you could just take the derivative of this to check it, and you would get that. Okay? So a couple ways to do these. Okay? I always like this method. That's kind of the way I kind of always learned it, so that's a little bit more aesthetically pleasing to me, but your choice on that one. When we get into separation of variables, though, you won't have any choice. We'll have to apply that method. Okay, here's another one. Now, this was a particular solution. This was the first ones were a general solution. Now, this is going to be what they call an initial value problem explicitly, or a particular solution to this differential equation. Particular because that means we've got a point, so we can narrow it down. This is just a family of curves. With this information, I'm going to be able to narrow it down to one curve. So again, the derivative is equal to 2e to the x minus cosine of x. So I put the dx over here, and then I integrate it in one step. So I saved one step. Maybe that you might want to do that. Be willing to use the integral setup. But anyway, these kind of the integral of the derivative is just y, so it just kind of cancels each other out. So y equals this antiderivative, and the antiderivative of e to the x is just e to the x, so that's easy. And the antiderivative of the cosine of x is the sine of x. In other words, the derivative of sine equals cosine, such as the sine of x, plus c. Okay, so that was pretty easy, just by doing the antiderivatives. And then when y equals 3 when x is 0, so every time I see an x I put a 0, and every time I see a y I put a 3. So y is 3 when x is 0 plus c. Well, e to the 0 is just 1, so I've got 2 times 1. Sine of 0 is 0, and plus c. So that's going to go away. If I subtract 2 from both sides, I end up with c equals 1. I put this back into my equation up here. Instead of writing c, I write 1, and there's the exact solution for that differential equation, or the particular solution. Okay? All right, so those should be pretty straightforward. 11 through 19 should be pretty much like that. On 21 and 23, they tell you your answer will include a definite integral, and these you can't find antiderivatives the traditional way. So I will give you a little hint. See example 4 on page 297, and that's going to give you kind of the method that you would do 21 and 23. So take a look at those. And on page, that example 4 on page 297, and that should help you figure out how to do those. Okay? And again, I get some solutions up on these shortly. Okay? Hope that helps.